There's Earth. Hold on a sec. There's nothing. I thought the dog knocked something over. Okay. Here is my geostationary orbit around the Earth. And what I wish to do is move my satellite, and let's say that my satellite is right here. And I'm looking from above. This is the eastward direction. So we're counterclockwise is to the east. And the question is, I want to move it 45 degrees to the east. So I want it to end up here when the previous sub-satellite point is back here. So what is it I need to do? I need to put it into an orbit such that it goes around more quickly. And how many times 45 degrees are in 360 degrees? So 360 minus 45. So I need the period of the new orbit to be, so I'm going to call it orbit number 2. Period of orbit number 2 has got to be 0.875, so 7/8 times the period of the geostationary orbit, which is orbit number 1. So this is orbit number 1. And the red orbit here is orbit number 2. Okay. Orbit number 1 has a smaller semi-major axis. I'm sorry, orbit number 2 has a smaller semi-major axis than orbit number 1. So it's going to be going along a lot faster. So we need the orbital period of this thing to be this. What was the orbital period of a geostationary satellite? It was 0.875 times let's see, I have all these data. Here we go, 86,164 seconds. So 0.875 times 86,164 seconds. So the period is 7.539 times 10 to the 4 seconds. So this red orbit will go all the way around in the time that it actually takes. Let me erase this. In the time that it takes the sub-satellite point on the Earth to be right there. And this is 45 degrees. Did everyone see how I figured out what the period of the second orbit has to be? It needs to be, there's 45, 360 minus 45 divided by 360. is what the period has to be. So if I wanted to move it 10 degrees, it's 360 minus 10 divided by 360. Okay, times P1. Okay, so now I know what P2 is. I know what A is, don't I? A has to be equal to P2. This is A2. It has to be P2 times the square root of gamma for the Earth divided by 2 pi to the 2/3 power. And gamma for the Earth, you remember, is 3.99 times 10 to the 14. So Adam, work out what A2 is for me.
Is it about 38.5 million?
I don't know. What is it? Yeah. So you think it's about 3.85 times 10 to the 7, right?
Yeah, I think so.
Okay, I think that's right. Very good. Okay, now we know A. What are the other things we want to know? Well, we'd like to know what the eccentricity of the orbit is. We can calculate that because we know that the radius at apogee is this distance right here. Isn't that right? This distance is perigee. This distance is apogee for orbit number 2. But I know that distance. That's the orbital radius of the geostationary orbit. So RA equals 42,000 I'm sorry. Yes, 42,164 kilometers. And that must equal, so it's apogee 1 plus the eccentricity times A2. So E is equal to RA divided by A2 minus 1. So A2 is the number that Adam just calculated. And RA is just the radius of the geostationary orbit. That's this distance here. So Benjamin, tell me what the eccentricity of this orbit is.
I got 0.09.
Okay, so 0.09. Okay, great. Now we know everything about this orbit because we know its semi-major axis and we know its eccentricity. So I can determine what the speed here at apogee is. The speed at apogee is the square root of 1 minus E over 1 plus E gamma over A. Okay, and this A is A2. So Truck, why don't you calculate the velocity at apogee for us?
I don't know if this is right. I got 29, 37, 165.
Sounds right to me. Now, what was the speed of a satellite geostationary orbit? Was 3.075 times a kilometer a second, right? Actually, I'm not sure that's right. Let me work it out, okay? So 1 minus 0.09 divided by 1 plus 0.09. Yeah, I got the same answer essentially. Okay. So that's the speed here. Now, what have I got to do? In order, at this point, I want to fire my rocket forwards. What does that do? That slows down. And because I slow down, I go into this inner orbit. So how much delta V do I need in order to do that? Well, my delta V that I require is going to be, and I'm going to put it in an absolute value, 3.075 minus 2.938 in kilometers per second. So 137 meters per second. Okay, now when I come back around, I need to have the exact same delta V, but in the other direction. I need to speed up to go back into the geostationary orbit. So my total delta V is equal to 274 meters per second. Now, how much oil do I use for that? Let's say my satellite initially is 2,000 kilograms. Well, I know that M initial over M final is equal to E. No, I'm sorry, that's wrong. Final over M initial. From the Tsiolkovsky equation, what do I have? M final equals M initial E to the minus delta V over V rel. And what is V rel? V rel is the specific impulse times G. And you've seen this before, right? Way back in chapter 8. So the specific impulse I told you was 325 seconds. So 325 times 9.8. That's 3,185 meters per second. So 2,000 times e to the minus 274 divided by 3,185. So my final mass after I do this maneuver is 1,835 kilograms, which means that I had to use 165 kilograms worth of fuel. So the fuel used for this maneuver is 165 kilograms. That's actually a lot, right? I can't do too many of these maneuvers before I'm going to run out of fuel. So if I wanted to move the satellite 45 degrees, which is a large distance, a better way to do it would be to do it in a number of orbits instead of just one. So let's say instead of moving 45 degrees all in one orbit, I'm going to move 5 degrees in 9 orbits. Well, then my period has only got to be 360 minus 5 over 360 times P1, and run through the calculation exactly the same. I'll use a lot less fuel, but it'll take a lot longer to do the maneuver. So this maneuver takes 7/8 of a day, the way we do it originally. It'll take 7/8 of a day. To do it in 9 orbits is going to take almost 9 days before it will come to the subsatellite point that you want. Okay, is everybody clear on how to do this phase maneuver?
I had a question.
Go ahead.
For the delta V, where did the 3.075 come from?
Oh, that is the speed in this original geostationary orbit.
Okay.
This is a 3.075. This is the 2.938 kilometers per second. So the delta V is the same at the beginning and at the end of the maneuver. It's just in different directions. At the beginning of the maneuver, you slow down by 137 meters per second. That drops you into this orbit. When you get back here, you have to speed up to 3.075 to get back into the original orbit. But when you do that, the original subsatellite point is behind you now. Okay,
I do have one question, Professor.
go ahead.
How did you get the number of 274 meters per second and the number of the fuel used?
274 is twice that,
Okay.
because you have to have this delta V at the beginning and you have to have this delta V at the end. So you add the delta V's together to get 274. Now you put in the 274 into the Tsiolkovsky equation.
Okay. And how do you calculate the fuel used at the end?
Oh, well, I started out with 2,000 kilograms. I end up with 1835. That means I must have used up 165 kilograms.
Oh, okay. Thank you.
Okay, you're welcome. Good. Okay. Well, this is complicated. I admit this is complicated. So let's see what the next question is. Oh, describe a Hohmann transfer that connects Earth with Saturn. What are the necessary delta V's and how long does the journey take? All right, now we're doing something different. Now we have the sun at the center. And, ooh, that's not right. We have the orbit of Earth right here. And then we have the orbit of Saturn. Okay, now we need an orbit that connects these two. And so it's going to look something like this. Okay. So orbit number 1 is the Earth's orbit. Orbit number 2 is the transfer orbit. And orbit number 3 is the orbit of Saturn. So we want to go from Earth, or from near the Earth, which is orbiting around the sun, to orbiting around the sun near Saturn. So basically we're doing a Hohmann transfer between Earth orbit and Saturn orbit. A little bit more than that, because you got to worry about the fact that you're going around the Earth and you want to go around Saturn, but we'll ignore that for now. Okay, well, what do we know? Well, we know that the radius of orbit number 2, at perigee for 2 is equal to the radius of the Earth's orbit. And we know the radius of orbit number 2 at apogee is equal to the orbit of Saturn. So what is the semi-major axis of orbit 2? Well, it turns out you can solve this in a number of different ways. Let me show you different ways to do it. So the orbit at perihelion has to be 1 minus E times A. And at aphelion is 1 plus E times A. Now, since you know these two numbers, the radius of the Earth's orbit and the radius of Saturn's orbit, you've got 2 equations and 2 unknowns. Solve for E and A. I'll tell you right now, A is going to be equal to the average of R1 plus R2. And E can be calculated in more than one way. Let's say E is, in this case, is going to be R2 over A minus 1. So now we know for orbit 2, we know A2 and we know E2. So we know everything. We know the period of orbit 2 because we know the semi-major axis. And remember, the period is equal to 2 pi A to the 3/2 power divided by the square root of gamma. But this gamma is not the gamma for the Earth. It's the gamma for the sun. Because all 3 of these orbits are Kepler orbits around the sun. Okay, now we know the period. I know how long the journey is going to take. It's going to take 1/2 of the period, isn't it? So I start here and I end up here. That's 1/2 of the period. That's how long the journey takes, and it's quite long. I don't remember exactly how long it is to go to Saturn. Let's see. Okay, it takes a little over 6 years. So to do it in this manner, which is not the only way, it takes 6 years to get there. It's got a 12-year period for orbit 2, so it takes 6 years to get to the orbit of Saturn using a Hohmann transfer. Right, now I'd like to know, what are the delta V's required? There's going to be a delta V1 here, in which case I'm going to have to speed up, and there's going to be a delta V2 here, in which I also have to speed up, because the semi-major axis of orbit 2 is greater than R1, but it's less than R. I made a mistake. This is R3. This is R3. And this is R3. Sorry about that. I meant Saturn here and here and here. That's orbit 3. So the semi-major axis of orbit 2 is less than R3, but it's greater than R1. So we're going to speed up in both cases in order to enter the transfer orbit and then to enter Saturn's orbit. So what is delta V1 for orbit number 2? Well, delta V1 for orbit number 2 is, in absolute value, is going to be the square root of, this is perigee, 1 plus E over 1 minus E, gamma over A, and that's E2 and A2, minus the velocity of Earth in Earth's orbit. So you have to figure out what the velocity of Earth is in its orbit. But that's easy. Assume it's a circular orbit. V Earth is just equal to square root of gamma over the radius of Earth's orbit. So now you've got delta V1. And what's delta V2? Well, delta V2, I'm going to put in an absolute value, is the square root. It's at apogee. So 1 minus E over 1 plus E gamma over A minus, let's see, that's going to be now minus the velocity of Saturn in its orbit. But I got to put this in absolute value. I did it backwards. So now I know my delta V's. If I want to know how much total fuel I use the Tsiolkovsky equation, and delta V's are always additive for the Tsiolkovsky equation, which is a consequence of the exponential function, the properties of the exponential function. Okay. Does anyone have any questions on how to do a Hohmann transfer? You have a mastering physics problem in which you're asked to do a Hohmann transfer between the Earth and Mars. And it turns out it takes about 2 years, I believe, to go from the Earth to Mars using a Hohmann transfer. Then you have to wait almost a year before the Earth and Mars are in the correct positions so that you can do another Hohmann transfer to get home. So going to Mars and back is like a 5-year journey or something. But you'll know the numbers when you work them out. I may have misremembered the numbers. So going to Mars is a big deal, much more difficult than going to the moon.
Just clarification for delta V2, we're still using E2 and A2, right?
Yes, because
Okay.
it's the difference between the speed in the second orbit and the speed in the third orbit.
Okay. Thank you.
So this gamma is for the sun, but this E and this A is for orbit number 2. They have to figure out what the speed of Saturn is in its orbit, but you can figure that out. Okay. Okay, for number 5, I ask you for the escape velocities for various planets. Well, you know how to calculate the escape velocity. So let's calculate the escape velocity for Jupiter. So here's Jupiter. Here's the mass of Jupiter. Here's the radius of Jupiter. My escape velocity here. So I get minus g m of Jupiter over the radius of Jupiter plus 1/2 escape velocity squared equals 0. That's an E right there, not a 2. So escape velocity is just 2gm over r square root. So you can look up in your book what the mass of Jupiter is. So the mass of Jupiter is 1.90 times 10 to the 27 kilograms. And you know what G is? The radius of Jupiter, the radius of the planet, not its orbit, is 6.99 times 10 to the 7 meters. So I'm on. Go ahead and calculate what the escape velocity for Jupiter is for me. Okay, so 2, did I solve it correctly? Yeah, I did. 2 times G, and G is 6.67 times 10 to the minus 11, times 1.9 times 10 to the 27, divided by yeah, so the escape velocity is, okay, so the escape velocity is basically 60.2 kilometers per second. Almost 6 times Earth's escape velocity. It's much more massive, but it also is much bigger. Okay, good. Let's go to number 7. So there's a comet. I actually looked it up. There is a comet Kowalski. The comet has a period of 68.4 0.8 years. So it's in an elliptical orbit. So somebody figure out how many seconds that is. We also know that the perihelion distance is 7.084 AU. And an AU is the distance from the Earth to the sun, which is 1.5 times 10 to the 11 meters. So somebody figure out what those numbers are.
So I have for the period is 2.17 times 10 to the 9.
Very good. And who has the radius at perihelion?
I think I have 1.05 times 10 to the 10 times 10 to the 12.
Is that right?
Yeah.
Okay. Now, we want to characterize this orbit. So the first thing we'd like to know is the semi-major axis. Well, that is the period times the square root of gamma divided by 2 pi to the 2/3 power. But gamma is G times the mass of the sun. And the mass of the sun is 1.99 times 10 to the 30. So G times 1.99 so it's 1.327 times 10 to the 20. So Alvaro, it's your turn. Plug in and determine what the semi-major axis A is. Okay, it doesn't look like Alvaro is with us. Louis,
Yeah.
go ahead and calculate A for us.
I got 1.2 times 10 to the 8.
Meters? No, that can't be. It's got to be greater than the radius at perihelion. Okay, let's work it out together. So 2.17 times 10 to the 9 seconds times the square root of 1.327. Okay, I get 2.51 times 10 to the 12.
That's what I got.
Okay, do you know what your mistake was, Louis?
Oh, yeah, I see it. I plugged 68.8 rather than 2.17.
That'll do it. Okay. All right. Let's calculate the eccentricity. Well, I know that R at perihelion is 1 minus E times A. That means E has got to be 1 minus R at perihelion divided by A. So Aurelio, you want to go ahead and calculate that for us?
Okay, can you repeat the question one more time?
Yeah, calculate E for us. Right here, calculate that. Mm.
0.58.
Wow. Okay, that is an extremely eccentric orbit, right? That means the distance from the center to the focal point is almost halfway to the edge. Okay. And what else do we want to know? What's the specific energy of this orbit? Remember the formula for specific energy? So, Tuan, I haven't called on you. Would you calculate the specific energy for us, please? All right. Aman, would you do it? I made a mistake. It's gamma over 2A. Put in scientific notation with 3 significant figures. What is it? And the units of this are joules per kilogram because it's specific energy of the orbit. Notice that we have no way of determining the mass, and from this analysis, we have no way of determining the mass of this comet. We don't, the mass of the comet doesn't appear anywhere in these formulae, do they? Does it? A body can be on this orbit and have any mass. Okay. We don't need to worry about angular momentum. What else do we want to know? Okay, the orbital speed at perihelion and aphelion, we've done this 100 times, right? At perihelion, 1 plus E, 1 minus E, gamma over A. And reverse these two signs for aphelion. Okay, good. Now, I want to point out something to you. Knowledge of the orbit doesn't tell us anything about the mass of the satellite or planet or whatever it is that's orbiting. In order to know the mass of the satellite, we need to have something orbiting the satellite. So we know the masses of the planets because the planets all have satellites. That's not entirely true. Mercury does not. Okay, so Mercury is a hard case. Oh, neither does Venus. Okay, but with those two exceptions, lots of satellites, we can figure out what the masses are by knowing the orbit of the satellite. Why is that? Because in the equations for the semi-major axis as a function of the period, this gamma is the primary. So if we know the period and the semi-major axis of a moon of Mars, then that tells us what the mass of Mars is. But we don't know the masses of any asteroids because we've never observed any asteroid that has a satellite. Now, that's not completely true. About a year ago, I think, an asteroid was discovered that had another little tiny asteroid going around it. And by observation of that satellite, we figured out what the mass of the asteroid was. But that's the only one that we know. Now, how we know the mass of Mercury, I am not really sure, since it has no satellite. Don't know the answer to that. That's something you can look up and find out how it's done. Okay, so this is orbitology, at least at this level. I hope you enjoyed it. We need to move on to chapter 14. So let's do that after a little break. Let's meet again at 3:15. So I'll see you again at 3:15. Sit up there. Yeah. Okay. Let's move on. Well, hold on, we have a minute. All right. So does anyone have any questions on anything? All right. Okay, so we're going to begin our discussion of harmonic motion. Let's consider as our basic problem a mass on a spring. And let's say it's on a frictionless surface going back and forth. The mass has mass m, the spring has spring constant k. Now we know the force law is Hooke's law, F equals minus kx. But F is also equal to what? ma, which is also equal to m d squared x dt squared. So putting it all together, we get a differential equation for the equation of motion. And that is d squared x dt squared plus k over mx equals 0. This is the basic equation of simple harmonic motion. Anytime you have an equation that looks like this, you have effectively simple harmonic motion. Now, what is the solution to this equation? Well, let's think about it a little bit. We could do a formal solution. Let's not worry about that. Let's say that x is a cosine. I differentiate the cosine, I get minus the sine. I differentiate minus the sine, I get minus cosine. So basically, the sines and the cosines are functions such that the second derivative will cancel out the original function. But you got to worry about this constant here. It turns out the solution is some constant a times the cosine or the sine, you can use either one, it doesn't matter, omega t plus a phase angle delta. Now this phase angle determines where the motion begins in time. This a is the amplitude. Omega is the radian frequency in rads per second. And it turns out omega is equal to the square root of k over m in radians per second. So it's a kind of frequency. Okay. Now, we call a the amplitude and delta is the phase constant. Let's look at a cosine function. Let's say it looks like this. Well, the amplitude A is this distance. It's also this distance. I didn't really draw it right. And in this instance, since it's equal to 1 at t equals 0, the phase constant delta is equal to 0. So adding in the phase constant just moves this thing back and forth on the x-axis. Well, this is x, and this is t. I should have made that clear. Okay? Now, if the motion is periodic, and the fact that the motion is periodic, we're going to use to calculate its frequency. So, you know what, I need to redraw that. So let's say we have something that looks like this. The period of the motion, I'm going to use capital T to stand for the period, is the time from one peak to another peak. This is T, and this is X. Now you could pick any point in the motion, and then when the mass returns to that same position, then that's the period. The time interval was the period. So since we have X as a function of time equals X at T plus the period, and this is true for any time T. If I add one period, all I do is I'm back where I started. Then I can write this as A cosine omega T plus phi equals A cosine of omega little t plus omega big T plus phi. Now, look at this carefully. These two things are equal. That tells you something about omega t. If I take the cosine and I add 2 pi radians, aren't I back where I started? Think about the circularity of the cosine function. I start here, I go around 2 pi, the cosine is the same. So that means that omega t must equal 2 pi. So omega is equal to 2 pi divided by the period in seconds. So 2 pi radians divided by the period in seconds. Now, the frequency, little f, is 1 over the period. Let's say that I have 2 oscillations in 1 second. So the period is half of a second, and the frequency is 2 per second. So the frequency is 1 over t. So it's usual to write this as 2 pi times the frequency f. And f usually is given units of either hertz or cycles per second. So let's write that down. Omega is in rad per second, and f is hertz or cycles per second. Okay, so that tells us what omega is. Now, okay, so let's assume we know the solution for our simple harmonic oscillator. X of t equals A cosine or sine, you can use either one, omega t plus my phase angle delta. Did I use phi earlier? And now I'm using delta. It doesn't matter, it's just a symbol. Here, let's just use phi. Okay, now what is velocity as a function of time? Well, that is dx dt. That's going to be minus A omega sine omega t plus phi. And the acceleration as a function of time is going to be dv dt. So that becomes minus a omega squared cosine omega t plus phi. Now we also have F equals minus k times x, and the acceleration is equal to F over m, which is going to be minus k over m times x, which is a cosine omega t plus phi. But these two expressions here are identically the same. Why? Because omega squared is equal to k over m. Okay, so it all works out. Now, let's say that I know my solution is this, but I don't necessarily know A, and I don't necessarily know phi. In order to determine A and phi, I need to know two initial conditions. I need to know X I need to know X at t equals 0. I need to know that. And I need to know V at t equals 0. If I know those two things, then I can determine A and phi. Let's go ahead and symbolically call this x0, and let's symbolically call this v0. Now, I know that x at t equals 0 is x0, and that must be equal to a times the cosine of the phase angle phi. And I know that v at t equals 0 must be v0. But v0 is equal to minus a omega times the sine of phi. Well, where did I get this? Right there. Where did I get this? Right there. Just plug in t equals 0. Okay. Let's solve these simultaneously. So I'm going to get, let's divide v0 by x0. So I'll get v0 over x0 is equal to minus omega times the tangent of phi. So the tangent of phi is equal to minus v0 over omega x0. Actually, I want to put my minus sign in the right place, because when I take the arctangent, I need to know what quadrant I'm in. Okay, so depending upon the value of v0 and x0, I could be in any quadrant. Now, I know what phi is. Now I can calculate A. A is just x0 divided by the cosine of phi. All right, so let's do an example. So let's let M equal 100 grams. Let's let K for the spring equal 25 newtons per meter. Then omega is the square root of 25 over 100. That's 15.8 rad per second. Let's make sure that's right. That's not right. Oh, 100 grams, not 100 kilograms. Yeah. So that would be 0.1 divided by 25. Why are these notes wrong? So it's oh. Okay, that's right. It is 15.8. Okay. So it's a square root of K over M. So 25 over 0.1 square root. All right, now let's look at case A. Let's say that we have V0 equals 0. So it's not moving at t equals 0. And let's say that x0 is equal to 10 centimeters. Well, we know that phi is going to be the arctangent of 0 because, let's go back. We have the tangent of phi is V0 over omega x0, so that's the tangent of 0. So what's the arctangent of 0? Must be 0. So that means that phi is 0 degrees. Now what about A? A is equal to x0 divided by the cosine of phi, which is nothing but x0. So here is my mass going back and forth. In this particular instance, I start out here at 10 centimeters. I'm at rest. I let it go. And the amplitude of the motion is clearly going to be 10 centimeters. And the phase angle is got to be 0 because the solution here then is x equals 10 centimeters cosine omega t. When t equals 0, x is just equal to a, the 10 centimeters. Okay, let's do one with some different initial conditions. Let's let V0 equal 0.5 meters per second. And let's let x0 equals 0. Now in this case, when t equals 0, my mass is here at the origin, and it's moving in this direction with the speed 0.5 meters per second. So let's figure out what t and a are. So phi is equal to the arctangent of V0 over minus omega x0. that's basically infinity. So what angle gives me an infinite tangent? Louis, what angle has an infinite tangent? Benjamin, what angle gives me an infinite tangent?
Is it 90?
90 degrees. Okay, very good. Now, I've kind of got a problem here because A is equal to x0 over the cosine of 90 degrees. So it really doesn't work. However, I can also use this equation, and I can write A is equal to minus V0 over omega sine of phi. So I can use either equation. And in this case, I need to use this because phi is 90 degrees. So I have A equals minus V0 over omega times the sine of phi. What's the sine of 90 degrees? The sine of 90 degrees is 1. So A is equal to minus 0.5 meters per second divided by omega, which is 15.8. So the amplitude is actually very small here, isn't it? The amplitude is actually 3.165 centimeters. But it's negative. So that means in this case, here, my x is equal to minus 3.165 times the cosine of omega t plus 90 degrees. All right. Now, if you're bothered by the negative sign here, don't be. It doesn't matter. The maximum extension of the mass is just still going to be 3.165 centimeters. This minus really just affects the phase. You can get rid of the minus by changing the phase angle, but I wouldn't bother. Just leave it like that. So that's a perfectly good function. I can plug in t and I can find out what x is at any moment. Plug in t equals 0, cosine of 90 is 0, x is 0 at t equals 0. Okay, all is well. Okay. It turns out that minus the cosine of omega t plus 90 degrees is equal to the sine of omega t. So you can change this to be 3.165 sine omega t, if you want. Okay, so that's the basics of simple harmonic motion. Let's look at energy in simple harmonic motion. Well, first of all, does anyone have any questions about anything we've done? Okay. Now, the potential energy, U, for the oscillator, is going to be 1/2 kx squared. That is going to be 1/2 k times a squared times the cosine squared of omega t plus whatever the phase angle happens to be. Notice how similar this looks right here. Look at this part of the term right here. This looks just like this, excuse me, just like the potential energy of a mass on a spring that's been extended at distance a. Well, that makes sense. The maximum value of the potential energy is 1/2 ka squared because the maximum value of the cosine is 1. And we expect that to happen. We expect that when we're at the maximum extension, our potential energy is a maximum. So that makes perfect sense. Okay, that's good. Now, what is the average potential energy over a cycle? Well, it turns out the average value of the cosine squared is equal to 1/2. Here's the cosine squared. The average value of that is 1/2. You can calculate that if you want, but you can just take my word for it. So the average value of the cosine squared or the sine squared over one period is equal to 1/2. That means the average potential energy is 1/4 ka squared. Now, what about the kinetic energy? Well, the kinetic energy is 1/2 mv squared. That's equal to 1/2 m. And what is v? Well, v is minus a omega. So square that, we get a squared, omega squared, sine squared, omega t plus phi. And what is the average value of kinetic energy? Well, the average value of the sine squared is 1/2. So that's 1/4 m a squared omega squared. But remember, omega squared is k over m. So the average value of the kinetic energy is 1/4 k a squared. So what am I saying? I'm saying that on average, the kinetic energy and the potential energy are equal. Over the course of a period, the average kinetic energy is equal to the average potential energy. The total energy is equal on average, is equal, so let's write that, E total on average is just going to be potential average and kinetic average. It's going to be 1/2 ka squared. And that makes perfect sense because the maximum value here is 1/2 ka squared. So add to that the maximum value of k, and then divide by 2, and this is what you get. Okay, so that's energy. All right, does anybody have any questions? Here's what I want you to take away as far as energy is concerned. On average, for a harmonic oscillator, over time, half the energy is going to be potential and half the energy is going to be kinetic. Add those two together, you get the total energy on average, and that's 1/2 Ka squared. Okay. Now let's look at an example of a simple harmonic oscillator that's a little bit different from the mass on a spring. But remember, if the equations are the same, it's going to be a simple harmonic oscillator. So let's say I have a mass, which I'm going to pretend is a point mass, M, on a light string of length L. And this thing is going to swing back and forth. That's a simple pendulum. Well, it turns out a simple pendulum is an example of a simple harmonic oscillator, sort of. So let's write down the torque. What is the torque on this mass? Well, the only torque is the gravitational torque. And the gravitational force in this direction is mg sine theta, where this is the angle theta. So that force is mgl sine theta. Only is it a negative torque or a positive torque? Well, if theta is positive, the torque is negative. If theta is negative, the torque is positive. So I need to put a negative sign there. But that, from Newton's second law, is equal to I alpha. And alpha is equal to d squared theta dt squared. But now what is I? For a point mass, I is ml squared. So here's my equation for a simple pendulum. ml squared d squared theta dt squared plus mgl sine theta equals 0. And if I divide through by ml squared, what I'll end up with is g over L sine theta. So I'm going to write that again. D squared theta dt squared plus g over L sine theta equals 0. This is not a simple harmonic oscillator. Adam, can you tell me why? How is this equation different from the harmonic oscillator equation? We had d squared x dt squared plus k over mx equals 0. How is it different? But look at them. The theta and the x don't signify. There's no difference, and the k over m versus g over L. They're of the same exact form, except what?
That sine theta is limited.
That's right. There's a sine theta here instead of a theta. So this equation is sometimes referred to as the mathematical pendulum. It is a very difficult equation to solve. In fact, excuse me, there is no known closed form solution. So you make various levels of approximation. The easiest approximation is if theta is small, then sine theta is approximately equal to theta. So provided the amplitude here is small, then we're going to replace sine theta with theta, and I'm going to just do it. And now I have the equation for the simple harmonic oscillator. And my solution by inspection, because you know what the other one's solution is, so you know what this is going to be theta as a function of t is equal to some amplitude, which is an unknown constant that you need to solve for given initial conditions, cosine omega t plus phi, where phi is another constant that you need to evaluate using initial conditions. And omega is the square root of g over L. Notice that the frequency, and therefore the period, does not depend on the amplitude. So a simple pendulum that I displace a little tiny bit and let it go, that same exact pendulum, I displace it more and let it go, and it's going to have the same period. It doesn't depend on the amplitude. It only depends on L, the length of the string. And everything about that I've said earlier about a mass on a spring is identical to what we could say about this pendulum, because they're the same thing. They're both simple harmonic oscillators. By the way, we're going to refer to simple harmonic oscillators as SHO. So you'll see that probably in the book, and you may see that, I don't know. In any case, it's common. Okay. Now, the simple pendulum is different from a physical pendulum, but they both undergo simple harmonic motion provided the amplitude is not too big. And by the way, as a rule of thumb, theta should be less than about 30 degrees for reasonable accuracy for this approximation. This is actually stretching it a little bit. Okay. Let's look at a physical pendulum. A physical pendulum is some arbitrarily shaped body that is supported at a pivot point and allowed to oscillate. And let's say that the center of mass is right here, and that distance from the pivot to the center of mass is equal to L. Now, how can we analyze this? Well, the gravitational force acts at the center of mass. And that is mg sine theta, where m is the mass of the physical pendulum. That means that the torque is equal to minus mg times L sine theta. But notice L is not the length of the thing, it is the distance from the pivot point to the center of mass. So if you pivot it at the center of mass, it's not going to oscillate. In fact, let's change our terminology. Let's call this H. So H is the distance from the pivot point to the center of mass. Well, this torque must equal I times d squared theta dt squared. Let's make the approximation that sine theta is approximately theta. And now my equation is d squared theta dt squared plus mgh over I times theta equals 0. So Andreas, what is the omega of a physical pendulum?
Omega is going to be,
Excuse me. Well, you can tell from this, d squared x dt squared plus k over mx equals 0. And omega in that case is the square root of k over m. So what's omega have to be here? Just look at it and see.
that would
What
be
the
the square root of mgh over I.
Exactly. Okay. Now, this has the same units as G over L because I goes like mr squared or mh squared or something. Notice that H will be different depending upon where I pivot it, and I will be different depending upon where I pivot it as well. Now, let's ask this question. What is the length of a simple pendulum of the same mass m, although mass doesn't actually matter? What is the, excuse me, what is the length of a simple pendulum that has the same frequency as the physical pendulum? Well, there, what we need is we need the square root of mgh over I must equal the square root of g over L0, where L0 is the length of a simple pendulum that has this same period, and that implies that L0 equal what? Equal mh over I. Nope, sorry, other way around. I over mh. Yes, I over mh, I'm sorry. What am I thinking? Now, if you look at this, this is the exact same formula as the formula we derived for the center of percussion. So another name for this L0, which would be some length, let's say here. Another name for L0 is the center of oscillation or the center of percussion. They're the same thing. Go back and look at the formula, you'll see it's exactly the same. Now, what is special about L0? Well, if my pendulum is supported at that point, I get the same period if I support it at that point. So the center of oscillation is the place where I can support the body, and the frequency of the oscillation will be exactly the same as up here. Okay, that's kind of, oh boy, that's it. Okay. Okay, that's a lot. Does anyone have any questions? Let's do an example. Let's say that we have an index card. Let's say we've cut it into a square. Really want this to be black. It's not going to do it, is it? Okay, that looks about square, doesn't it? All right, let's say that I pivot it right there on the edge somehow, and I let it swing back and forth. Well, the center of mass of the card is obviously right here. So if I have a side A, then what is this distance right here? This distance is H, and this is A over 2. That means A squared. Sorry. Is equal to, no, that's not A over 2. I'm sorry. No, that's not A over 2. What am I doing? Okay, this distance here is H, but it's the same as this distance. So A squared equals 2 times H squared, right? That means H is equal to A divided by the square root of 2. All right. So H is equal to square root of 2 over 2 times A, if you want to write it that way. Okay, now, what is the rotational inertia of this thing? Well, the rotational inertia is going to be the rotational inertia through the center of mass plus mh squared using the parallel axis theorem. So if I pivot it right here, I through the center of mass, here, plus mh squared. So we're going to have to look up in our table. And I think it's in chapter 9, right? Where is the, here it is. So for a square lamina through the center, I center of mass is equal to 1/12 m of a squared plus b squared, but b equals a. So this becomes 1/6 ma squared. Little a. Plus mh squared, which will be 1/2 a. A squared over 2, I mean, 1/2 a squared. Okay, so what is this? So 1/6, 3/6, so 4/6, so 2/3. Okay. I miswrote this. I center of mass is 1/6 ma squared, but I is that plus ma squared over 2. Okay, so rotation are 2/3 ma squared. So what is going to be the frequency here? It's going to be the square root of m g h over I. Go back and make sure we agree with that. So mg over I. And that's going to be the square root of m times g times a divided by the square root of 2. Now times I is 2/3 m a squared. So the mass cancels, and the a cancels with the square, and we get 3 over 2 times the square root of 2 times a. All right. Exactly in the form g over some length. Now if you put your pivot someplace else, well, h will change, and so will I. And so you won't get the same result here. Unless you make this distance between these 2 points equal to the center of oscillation. Okay. Anybody have any questions on this? I think we've covered just about everything.